Hello everyone. Today we will start with the unit 2, which is on MOSFET, metal oxide semiconductor field effect transistor. There are basically two types of MOSFET, that is P-type MOSFET and the N-type MOSFET. So MOS basically means metal oxide semiconductor. The upper metal layer which is used to connect with the other devices or with the external world, and the middle oxide layer which is made up of silicon dioxide, and the lower layer is made up of N plus P substrate, N minus P plus likewise, which is basically a semiconductor layer, extrinsic semiconductor, which is doped with pentavalent or with the trivalent uh, impurities for the intrinsic silicon dioxide silicon material, right? So now to distinguish between PMOS device and the NMOS device, we have P substrate and N diffusion implanted on the P substrate, and for the PMOS device we have N substrate and implanted with the P concentration, P diffusion in the layer. Okay, and to distinguish between the terminals, that is which is source and drain, right? Basically there are four terminals. Those are source, drain, gate, and the body contact or the substrate contact. That will be the fourth terminal. Okay, so now for the NMOS device, so the symbol for the NMOS device is like this, which you have drain, source, this is drain, this is source, and this is gate. So the arrow indicates, the arrow going outside indicates that it is the majority charge carriers are due to electrons and the current flow is due to the electron, and this is the fourth connection, that is body or the substrate contact, which is connected to the source terminal or for the lower potential for the NMOS device. And for the PMOS device, whereas this is the symbol where it indicates the arrow entering into the MOS device, indicating that the majority charge carriers are holes, the current flowing in the device is due to the holes, and this is source, drain, and this is gate, and the body or the bulk potential of the PMOS device is connected to the highest potential, preferably for the source. Okay, so this is just a symbol of the PMOS and NMOS device, whereas this is the physical structure what you see here inside the IC, the PMOS or the NMOS. Okay, so here for the NMOS device, where you have N diffusion on the P substrate, the source and drain terminal are determined because with respect to the potential. So if the any of the diffusion is higher potential, then it is determined as the drain, and if it is lower potential, it is determined as the source terminal for the NMOS device, and this is gate, which is connected to the crystalline polysilicon structure. Okay, and for the PMOS you have the source terminal connected to the highest potential, and the drain terminal will be for the connected with the lower potential, and this is gate connected to the crystalline polysilicon, right? So this is how you distinguish between the PMOS device and the NMOS device for the metal oxide semiconductor field effect transistor. Okay, so in this we will analyze how the device operates. Okay, there are basically two voltages what we are giving. So one is gate voltage with respect to the source. Okay, as I told, the source is connected to the lower potential, so the gate is connected to to the gate potential what we are applying to operate this MOS device. Okay, and here when we apply there are different fields, as I told, the gate voltage, which is basically the vertical field. Okay, and the another voltage what we apply is the drain voltage with respect to reference, which is source. This is basically a horizontal field. Okay, drain to source potential. Okay, from drain terminal to source potential, and the gate is gate to source potential, which is a vertical potential compared to the drain to source potential. Fine, and here in this with respect to the vertical potential, there are three different regions of operation, and with respect to the horizontal potential or horizontal electric field, there are three different regions of operation. So here first we will discuss about the vertical potential or with respect to the gate voltage. So when we apply a gate voltage, So for example, gate voltage is equal to or less than 0. That means if we apply a negative potential, what happens if we apply a negative potential for this gate terminal? So all the electrons will come and sit on the, if I apply a negative potential here with respect to source, and this body or the substrate contact for the NMOS device is also connected to ground or the lower potential, right? So when it is less than 0 or equal to 0, then this gate terminal are accumulated with electrons, and all the majority charge carriers in the P substrate will be holes, and all the holes will get accumulated in the P substrate here. Okay, so this is how the device orients its majority charge carriers according to the field. Okay, and this is called as accumulation. Okay, accumulation of the charges according to the field that we have applied, right? So, and when we increase the gate voltage, when Vg is greater than, when Vg is greater than 0 but less than threshold voltage. Okay, threshold voltage is the minimum voltage required to create a channel or for the conduction of the current in the MOS device. So when we give a small positive potential here, so what happens? So all the electrons which are minority charge carriers in the P substrate will deposit beneath the channel and forms the channel beneath the gate and forms the channel layer, and all the holes are repelled from the gate terminal and get deep inside the P substrate like this. Okay, and here, so all the electrons will get accumulated to the positive terminal what we have applied for the gate potential, and this layer what you have formed is called as depletion region. Okay, so this is depletion region corresponding to the gate voltage greater than 0 but less than threshold voltage. You have depletion region, right? Basically you have an electrons beneath the gate forming a channel. Okay, but what happens here, because of less potential, that is less than threshold voltage, so these are basically happens to be an immobile ions. They don't have enough strength to cross the barrier potential, and because of not movement of electrons or ions, there will be no current in this region. Okay, so when you give the gate voltage greater than or equal to the threshold voltage, what happens? All the region beneath the gate will be of higher majority charge carriers, will be the electron in this region. Okay, in this region it will be electrons, and you form a channel in this region. A channel is formed. Okay, and what happens? This being a P region has been inverted to the majority charge carriers happens to be an electron over here, which is basically an N region. So this happens to be an inversion region, inversion mode of accumulation, inversion mode of operation. Okay, so these are the different regions of operation with respect to the vertical field, that is when we apply the gate voltage, right? And now when we start applying, but when we apply the gate voltage, still the current will be 0. ID is the current which is flowing from drain to source, because next what we apply a the horizontal field which is drain to source potential, that is drain being positive and with respect to source or the reference. Okay, so the drain is at higher potential. So here the ID will be 0 if VDS is 0, because even though we have an electrons over here, there is no difference between these two terminals, that is drain and source, and hence there will be no current flowing in this channel. Okay, so now when we start increasing the horizontal field, that is VDS, when we start increasing, then what happens? There will be a difference in between the drain and source potential, and because of this difference in potential, the electron starts moving in the channel, and the electron starts moving towards the positive potential, that is towards the drain terminal. So all the electrons inside the diffusion as well as from the substrate or inside the channel will come towards the drain, will be moving towards the drain, and the current will be flowing towards the source ID, opposite in the direction of flow of electrons. So corresponding to this VDS, so we have different regions of operations again. So this is now, before we start giving the VDS, we have given with the particular gate voltage which is particularly above threshold voltage VGS, and it happens to be constant before you start giving the drain to source voltage. So now here what happens, if I draw the output characteristics for the MOSFET, this is VDS what I am wearing, and this is ID for a constant VGS. So the curve will be something like this. So that is for a constant VGS, right? So initially when I start increasing the drain to source voltage or the horizontal field VDS, so here the current will be 0, and when I start increasing greater than 0, what happens? The current start increases linearly with respect to VDS, and the VGS is anyhow constant, and this increases linearly up to certain voltage up till this point, which you call it as overdrive voltage. Okay, this is overdrive voltage, is the voltage VDS which is equal to VGS minus VTH, the overdrive voltage. From here onwards, what happens? There is no change in the current will not increase further linearly, it becomes independent of VDS. Okay, so now to determine this IV characteristics, we will come across what is the IV characteristics and what is the current equation corresponding to this linear region and saturation region. You will see that how this current becomes saturation after this overdrive voltage, which becomes an independent of VDS. That means even though if you vary the VDS, the ID will remain constant. Okay, so we will look onto this IV characteristics, that is the derivation of the current, drain current corresponding to different regions of operation, in the next class.